Here it says.
I've moved between the sign up and the
Munich, Cambridge, and she'll talk about revision theory of probability.
Yes.
Please.
Thank you very much. And it's very exciting for me to be here. It's quite a different environment to the ones I'm used to. So I'm a philosopher, and I'm used to giving philosophy talks. And so this is it is mostly still a philosophy talk. The technical bits are not that difficult, but hopefully it's of interest and shows a use of some concepts which there's some people have worked on revision theories in connection to set theory, particularly Philip Welch and Benedict Loewe. So yeah, this is a version of this where one now talks about a revision theory applied to a notion of probability, and some interesting considerations and modifications that become relevant in this framework. So first of all, what am I doing? So I'm considering a language which can talk about probability and it can talk about truth. But it can do more than just say things like the probability that the coin lands heads is a half. It can also say the probability function that's there is type 3 and it allows for self-reference. So many of you have probably heard of the liar paradox. This lambda here is the liar sentence. And this is a sentence such that PA proves that it's equivalent, lambda is equivalent to not true lambda. This is a sentence that says of itself that it's not true. And philosophers are particularly interested in this. Lots of discussions. Is it true? Is it not? What should one do with it? So that's the sort of sentence we'll have around. So more formally, everyone knows this, but just saying explicitly, the sentences are being coded into arithmetic. So this stands for the numeral of the Gödel number of the sentence lambda. I'll also be interested in things like, what is the probability of this sentence? This is something that hasn't been considered so much, but it's, there's been a little bit of work on it, and it's quite interesting that it can tell you some new things. I'll also be interested in this pi, which is a probability liar paradox. This says of itself that it has probability less than a half. And what I'll be doing to understand these probability and truth is to develop a revision theory. So for the truth, what you're trying to do is see, is it true, is it false? What features about truth can we know in this framework where there's self-reference? And similarly for probability, what probability do these sentences get? What sentences about probability are true? And we work that out by developing a revision theory. I'll say a bit more about, well, the idea of revision theory is you start off with some arbitrary hypothesis and you keep on improving it or modifying it until, well, throughout the ordinals. So, first of all, I'll skim through this quite briefly. This is more the philosophical introduction, is motivating these languages. So, in particular, these languages are interesting to the philosopher who's interested in describing probability, because there's certain things we really want to have in a framework that we can express. So for one thing, we want to have higher order probabilities. Things like Annie believes to degree 0.99, that Billy believes to degree a half that the coin will land heads. This is something that says something, so Annie's probability about Billy's probability. There's embedded probabilities, and they're working together. We want these in our language. And once you've got embedded probabilities of two different notions of probability, syntactically it's much smoother to also have Annie's probability about Annie's probability, so really higher order probabilities. Secondly, we want things like, we want to be able to quantify over sentences. So Annie is certain that Billy has some non-extremal degrees of belief. Annie is certain, there should be an equal one, that there is some sentence such that Billy has a non-extremal degree of belief in it. And that's not usually present in the operator probabilistic operator languages, which are usually studied.
Say that probability is 1.
Yeah, equal 1. Yeah, that's a typo. And once we have these, the most natural way to get these kinds of things is to formalize probability via a type-free probability predicate. But by standard diagonal lemma-style reasons, we get out these sentences which are equivalent to some fact about probability. And these can also be useful to describe situations which aren't usually describable in languages. So for example, this is an example from Hilary Greaves. Alice is up for promotion. Her boss is really an insecure type. And he only wants to give her the promotion if she's unconfident in herself. And the way he's going to measure this is by if she has a low degree of belief that she'll get the promotion. So that's a situation where she gets the promotion just if she has a low degree of belief in it. And assuming she knows the setup and believes the setup, then this is an appropriate way to represent that setup. So that's interesting, but there's logical kind of problems with analyzing these things. And that's what the revision theory is going to help us with. So I've mentioned already, but there's a few different notions of probability that are in play here. So first of all, what is probability? Well, you all know probability. Here I'm assigning probability to sentences, probability values to sentences. So here are the axioms of probability. In general, I'm only assuming finite additivity. There are some interesting things that happen with sigma additivity. So this is the principle of sigma additivity. Says the probability of some universally quantified thing is the limit of the probabilities of the conjunctions. Now, usually we know countable additivity from the probability of a union is the probabilities of it is the sum of the probabilities. Now, this is a probability applied to sentences. And this, in a way, sums up two things. It sums up, firstly, that the measure underlying it, the measure on the models, is countably additive. And secondly, that the models are all standard models of arithmetic. And then we get this thing. Well, that's sort of the way to think about it. So this will be something that I will sometimes discuss, but in general is not in the background framework. And so that's the formal notion of probability that's here. There's also a question of what are we meaning when we say the probability is a half. So there's lots of different things one could mean. These are ones that are quite often considered. The one I'm going to be focusing on here is subjective probabilities. This is something like degrees of belief of an agent. You go and ask someone, how much do you either how much would you bet with me to that the coin will land heads, or you just ask them, how likely do you think it is the coin will land heads? So that's one notion I'll be focusing on, but there's also another notion which comes into play here, which is semantic probability. That's kind of a not really a term that's been used, but I think it fits here. Something like degree of truth, how true these things are. And with sentences like the liar, it's not clear that they're either true or false. In a way, there's something weird about them. This can sort of measure their paradoxicality. And one thing that will come out here is the probability of the liar becomes a half, in some sense. So we've got these two notions of probability that are of interest, this subjective one and semantic one. And they're different, and they're saying different things. And corresponding to these two different notions of probabilities, we'll be presenting two different revision sequences, or two different styles. One gets us semantic probabilities. And the idea of this revision sequence is how often in the revision sequence is the sentence true. And that gives you the probability of the sentence. And that's the probability measuring how true the sentence is. But for example, that won't say things like the probability that the coin lands heads is a half. That's a different notion of probability that's in play. And that's the subjective one. And there we need to build that into the framework by having possible world structures in the background. So two different revision sequences will be doing two different interesting notions of probability. So that's what I'll do. I'll spend most of the time sort of setting up what revision sequences are and how one should define these two different versions. And then just discuss some results of these, present some theories, and conclude. So a revision sequence is kind of a sequence of extensions of truth and probability, where we're trying to determine what the appropriate extension of truth and probability are. And we do this throughout the ordinals. So first of all, I present the finite stages, and then discuss how to go to the limits. The transfinite successors are another interesting feature. So those are the three stages of presenting the definition. That's what I'll do. Bit more formal setup. So what I've got here is a background language, which at least contains arithmetic and some stuff about real numbers. And I extend this with a probability function symbol and a truth predicate. So a unary predicate and a function symbol. I'm not going to worry about things like heads and, I don't know, whether snow is white. That's fixed by some ground model. So you have a background model of the language, assuming it's a standard model of arithmetic in the real ordered field. This is really the setup for the semantic probability version. It gets a little more general for the subjective modal case. What we want is to determine the correct extension of truth and probability. Well, if we can't say, here's the extension, at least we can find out things about it. For example, the probability of the liar is a half, or snow is white is true. So what we do, we're trying to construct these extensions. An extension, well, we're calling it a hypothesis. This is some, assign some truth values to the sentences and some probability values. I'm restricting it to the interval, I'm just by fiat. That's not so important. So it assigns to natural numbers, which are codes for sentences, a truth value and a probability value. And with these hypotheses, we start off with some arbitrary hypothesis and we keep on modifying it. Revision sequence is a sequence of these hypotheses. Quick notation is it's just the alpha model, which has this ground model, and the alpha hypothesis, interpreting T and P. And the truth value is just 1 and 0, according to whether it's true or not there. So, first of all, how do we define this revision sequence? Let's start off simple. Let's start off just with the truth revision sequence. That's something that's been studied a lot. So, and even simpler, let's just look at the finite stages. So this lambda is the liar sentence. It says it's not true. At the first stage, you assign some arbitrary hypothesis. Okay, the one here has lambda is not in the extension of the truth predicate. Okay, you look at it and you realize, oh, therefore lambda is satisfied there. So at the next stage, lambda should be in the extension of the truth predicate. You say, well, lambda, therefore lambda is true. That's how you get from one stage to the next stage. And that's characterized by this. Something is in the extension of the truth predicate. Well, I mean, really, you should have the code of phi, but whatever. That's notation abuse. Something is in the extension of the truth predicate at the next stage if it was satisfied at the previous stage. So that's how you get the liar goes true, false, true, false, true, false. So now we know how to do truth in the finite stages. How do we do probability? Oh my gosh. Oh no, sorry. I can't read the hour from the minute hand. So here's something Hannes Leitgeb has considered this. He presents a sequence where he goes through the finite ordinals and gets to omega. And this is the relative frequencies revision sequence that he proposes. He says, the way you should work out the probability of a sentence is look at how often it's satisfied in the sequence before. So Pn plus 1 is the relative frequency of phi being satisfied in the models up to that stage. So for example here, liar was true here and false here, so its probability is a half. And this is the this is the semantic probability version. Doesn't tell you about probabilities of ground things like heads, just tells you about the paradoxical nature of sentences. Okay, so that's at least the finite stages of that. Let's look at what we do for the, he extends this to the limit stage, the omega stage, by taking a Banach limit of these things. I'll do something that's very, it ultimately relates to a very close proposal, but in its form is kind of different. So the possible world structures is what you need if you want to get things like probability of heads is a half. Here we take, here we're going to have a ground model where we sort of impose these probabilistic facts. So this is just a quantitative Kripke kind of structure. You've got a set of possible worlds. It's just some non-empty set. Can also be infinite. For each world, you've got an accessibility measure over the other worlds. I'm assuming it's defined on the whole power set. So, in particular, for certain structures, this will sometimes not be countably additive then, because I'm only assuming finite additivity, which is particularly okay in the degree of belief case, because there's arguments that people's degrees of belief just don't satisfy this infinite additivity. So anyway, it's a finitely additive measure defined on the power set. So for example here, this can see this world to degree 3/4 and this world to degree 1/4. And you've got facts about the ground, the base language already fixed. So here, coin landed heads, here it landed tails. It's a weird agent's beliefs about this. If it landed heads, she thinks it landed heads to degree 1/4. If it in fact landed tails, she's certain of that. But that's the way it goes. Now, here what we have to do is not only get the extension of truth and probability, for one world, or one extension of truth and probability, we have to say what the truth and the probability is at each world. So now our hypotheses just have one extra complexity bit. They assign to each world some truth value to every sentence and some probability value to every sentence. In general, the boldface versions that I'm using are just assigning to each world one of the non-boldface things. So now we're trying to work out the extension of truth and probability at each world. And we need to keep on updating that. So how does this updating process work in these probability cases where we've got this background structure? Now calculating probability for the successes is quite, obvious. You just use the accessibility relation. So the probability at the next stage is just how much that world can see other worlds where the sentence is true. So for example, here, heads is true here, heads is false here, at the 0th stage. It's satisfied here and not satisfied here. So at the next stage, the probability of heads is 3/4, because it can see one where it's satisfied to degree 3/4, one where it's not satisfied to degree 1/4. Okay. So you just use the background structure to tell you the probabilities. And that's a very simple successor stage, just applying this definition. And this is the sorts of definitions that fit much nicer into the original revision theory presented in, for example, Gupta-Belnut's book. Okay, so that's the two different finite stages. We've got the semantic one and the degree of belief one. My brain's gone. Okay, that's for the finite stages. Now the next thing I said we were going to do is say what to do with the limits. And here we go to the original revision sequence, which which is presented as a general revision, how to revise definitions, or revision theories of definitions which might be non-positive and have these kinds of features. First of all, why do we need to go into the limit stages? Well, I mean, we never did everything none of these finite stages have got everything correct. So for example, each stage has some t to the n is like t of t n times of 0 equals 0. At each stage, one of these things is not satisfied. But of course, 0 equals 0, it's true that 0 equals 0 arbitrarily many times. So we want that to be fixed. And so we need to go into the limit stage to do this. Here's how Gupta and Belknap say we should go into the limit stage. At a limit alpha, one sums up the effects of earlier revisions. If the revision process up to alpha has yielded a definite verdict on an element D, then this verdict is reflected in the alpha hypothesis. Otherwise, one is free to assign to D any element of X whatsoever. So their rule is, if a definite verdict has been brought about by the sequence beneath, limit ordinal mu, then it should be reflected at the mu stage. Okay, let's look at this for truth. Now, 0 equals 0, it was not in the extension of the truth predicate here, but every stage after that, it was in the extension of the truth predicate. So, it's what's brought about by the sequence beneath omega is that 0 equals 0 is in the extension of the truth predicate. So it should also be reflected in the limit ordinal, i.e. satisfied here. So if phi is stably true at limit ordinal, sort of beneath or in the sequence below limit ordinal, then it should be true at the limit ordinal. And if it's stably false, then it should be false. And we're not going to yet say anything about what to do otherwise. What does stable mean? It just means from some point beneath that limit ordinal, it was always true, up till that limit ordinal. So there's some smaller ordinal where from that stage onwards, up to the limit ordinal, it was always satisfied, true. So applying it to probability now, here's a simple case, same thing. What's the probability of 0 equals 0? Well, here's just a sequence applying what we said before. It's just, first stage got it wrong because it was a stupid hypothesis to put in, and then it, worked it out, and the probability was 1 all the way up. So this sequence yielded the definite verdict that the probability is 1. So we get probability is 1. So this works in this really simple case. But that's pretty much the only cases it works in. So here's an example. For example, it doesn't even get the probability that it's true that 0 equals 0 is 1. That probability converges to 1, but it never actually stays at 1 from some point. Here's an example for the liar sentence. The liar's probability goes 0, 1, a half, 2/3, a half, whatever. Converges to a half. But it's not brought about, it's not stable that its probability value is a half. But of course we want this sequence, it brings about that the probability is a half. So we should really also put the limit probability to be a half. So we need to modify this definition. This is the original one. If a definite verdict is brought about by the sequence, it should be reflected at the stage, where brought about means stable at that ordinal. Now, instead of looking at definite verdicts that are brought about, we're going to look at features of the hypotheses that are brought about. So instead of saying if a definite verdict is brought about, we say if a property of the hypotheses is brought about, then it should be reflected. Okay, and this is the reformulating their criterion. That's just any properties which assign a particular probability or truth value to a sentence. But we just said that's not enough, we need to do more. We should also look, for example, at intervals. If we say, if the probability is stably in some interval, then it should be in that interval, the limit stage. And that will get us the feature of the probability of the liar becomes half. And we should also have truth values being certain things. But now we've started to think about what properties we could focus on. Why not focus on as many properties as possible? So, what does as many as possible mean? Well, as many as possible is all closed properties. Open properties are going to act badly at limits. So, for example, the probability of some sentences less than 1 isn't something that should be taken over to the limit, because if it converges to 1, you'd want to put it at 1. So, let's consider this. Let's say any closed property that's brought about by the sequence beneath that limit ordinal should be satisfied at the limit ordinal. And that's the proposal I'm going to be considering. Depending on which version you're using, it'll be different kind of, the hypothesis space is different, but just using the product topology here. And brought about, for now we're considering a stable again. I will actually be considering nearly stable, but that's a discussion for a few slides later. So let's consider this more. What does this proposal get us? Here's this sentence, the probability converges to a half. Since all these properties are closed and stable, the probability will be a half at the limit. But sometimes it doesn't converge, but only sort of stays within some interval. So here, this is some kind of complex sentence, but it just basically says, stay in the interval. And that's what it does. And what's going to end up being brought about by this is that the probability should be between 0.4 and 0.6. But it's not going to say any particular thing about what it should be. What you can also do, another thing that's stable is, that's a closed property, is the probability of delta plus the probability of not delta is 1. That's a closed property. And it's brought about for this delta, in fact for any delta, or for any sentence, that's brought about by the sequence beneath omega. Just because that's an axiom of probability, all these finite stages are determined by relative frequencies. They're going to be probabilities. So what should be also satisfied at the limit stage is that the probability of delta plus probability of not delta is 1. And that's displayed by this example. But of course, being a finitely additive probability function is closed. And since since being a finitely additive probability function is stable, that will also be satisfied at limits. And similarly for t being maximally consistent. I'll say this more explicitly later, but that's a big step away from traditional revision sequences. Traditional revision sequences don't have that. They just have that the limit stage, they typically don't say that the limit t should be maximally consistent. Okay. Now we can apply the same definition. Those previous examples were for the relative frequency case. We can also apply it to the probabilistic modal structure case. And here we see obvious examples of certain non-convex properties playing a role. So here is an example with just one world and the liar sentence. So that whatever then the probability is going to be essentially just truth. It's going to be certain about what it says. So the sequence here just goes 0, 1, 0, 1, 0, 1. Because if it's satisfied at some stage, then it will be certain that it's satisfied at that stage, because it can only see itself. It's only considering itself as a possibility. And so then the probability will become 1. And then it turns out to be false, and it's certain of that evaluation, so then becomes 0, etc. And now the probability of the liar sentence at W is either 1 or 0. That's a closed property and it's stable. So at the limit, we're asking that the probability is also either 1 or 0. Now this is behavior that I'm not sure about yet, and I still don't know exactly what to say. Because this is kind of a feature of probability. We know that the coin will either land heads or it will land tails. But what we do in that case, we say the probability is a half because we're not sure which one. And you might want to say something kind of analogous here. The probability is either 1 or 0 at all the previous stages. But does that mean the probability should either be 1 or 0? Which one? Why not then the probability is a half? So maybe we want to restrict it instead just to convex sets, convex closed sets, where, I mean, the convexity is only a condition that would apply to the probability extension. So we just take the projection onto the probability side of things and ignore the truth side of things. And in fact, everything I'll say, I think, pretty sure everything I'll say will hold also if we weaken it to only considering convex sets. But that's, for now, I'm just going to leave that aside as an interesting thing to think about and continue with the original definition of any closed set. Now, also in the probabilistic modal structure case, you can have certain things like relationships between different worlds. So here we're considering the probability of the liar. There's two worlds, they can each see themselves, and now we've just got the same sequence. Oh. No, there's a cross and a dot here. Just because I was just saying at the first or 0th stage, probability of everything is 0, but the liar is in the extension of the truth predicate here, not in the extension of the truth predicate here. Haven't set it up explicitly here, but there's some kind of initial hypothesis under which, applying these rules, you'll get this sequence where they're doing this. And what's something that's brought about here is that the probability of the liar at the circle world plus probability of the liar at the cross world adds up to 1. And this is also convex now. It's just saying something about relationships between different worlds. It's closed and stable, so this is going to be brought about at the limit stage. So that's the proposal for the limit stage. One last thing to talk about is how to do the transfinite successors. For the modal case, that's just simple. That's just, we've got a definition, and the definition we gave for the finite case, finite successors, is just the same for the transfinite successors. You work out the next probability by looking at the background structure for the previous stage. But for the relative frequencies, it's not that simple. What we did for the relative frequencies at the finite stage was look at like how often the sentence was satisfied in the previous sequence, in the whole of the previous sequence. And now, once we're at the transfinite successor stage, it's not clear what the whole of the previous sequence, it's not clear how to take the relative frequency of the liar sentence being satisfied before omega plus 2. Here's one proposal. It's what I've been working with. There are some bad features of it. It says, when you're considering the probability at stage alpha plus 1, look at the finite sequence preceding alpha plus 1 from the limit ordinal beneath it, and take the relative frequency there. That's the kind of, it just does what you did in the finite stage, and in a way ignores the complication of the transfinite stage. So a bit more carefully then, you look at the limit ordinal, the maximal limit ordinal beneath alpha, and you just take the relative frequency of phi being satisfied in the sequence between that ordinal and the ordinal alpha. Right. So here's some weird features of this at any stage limit ordinal plus 1, the probability of any sentence is either going to be 0 or 1, because there's only one world. There's only one stage that you're considering that's beneath it. So here you only look at stage omega. Oh, it was satisfied, therefore its probability is 1. That's a really bad feature, I think, of it. But, okay, that's what I'm going with for now. There's an alternative that Leon Horston is currently looking at, where you look at arbitrary finite subsets, look at the relative frequency there, take some ultrafilter, and sort of sum it up using the ultrafilter. That's super interesting, but I'm not going to continue talking about it. And that's something that, yeah, that's a way I think we can take things up into these limits, do these transfinite successors in a nice way. But, okay, I'm not focusing on that. So what I'm doing, the transfinite successor in this version, is just looking at the finite sequence, maximal finite sequence up to that ordinal. So here's an example of, here's our current proposed limit rule. So it says, if some subset of the hypothesis is closed, or the hypothesis space is closed and stable in the sequence up to that ordinal, then it should be satisfied at the limit ordinal. Now, when we're using the relative frequency version, also at these transfinite successors, here's what happens with the Lyre. It does this kind of sequence we saw before, and it basically repeats the same thing between omega and omega plus omega, and then it repeats the same thing. Along each copy of omega, it converges to a half. Something that seems to be brought about by this diagram, or by this revision process, is that the probability is a half. Along each copy of omega, it converges to a half. And, I mean, that seems like a natural thing you might want to do to sum up this behavior, is to put the probability being half. So, to get this, what we're going to do is not look at what was stable. Stable meant there's some ordinal beneath it, such that from there onwards, it was always satisfying, or always in that set. So, for example, the probability is nearly a half. There's no stage beneath omega squared where that is always satisfied, because there's always going to be one where it goes back to 1. And this is particularly a problem because of the weird kind of transfinite successors we're using here. But even if we weren't using those kind of transfinite successors, one thinks such behavior might occur for some reasons. So there's nothing yet that tells us that the probability should be a half, but there is if we, instead of considering stability, consider near stability. So stability said it satisfies from some point onwards. Near stability says it's satisfied from some point onwards except for finitely many after each. Okay, it says there's some smaller stage such that from that stage onwards you can shift finitely often. You can do a finite shift, but then it's going to be satisfied from there onwards. So, for example, here the probability of the Lyre is less than 3/4. We go here, and then we do a finite shift. Well, it's a 1 shift, and then it's we sort of this kind of bit of it will satisfy that property. And so it just means we can ignore these weird things straight after limit ordinals. So if we consider this near stability, we will get the probability of the Lyre at omega squared is a half. So that's the definition I'm proposing. It says a relative frequency revision sequence has the normal truth stage. The probability is the relative frequency, and consider closed properties that are nearly stable and make sure that they're satisfied. Now, I'm not saying anything about what you should do when I'm not imposing any further restrictions than that. One might want to do that. Yeah. I'm just saying any sequence that satisfies these conditions is an appropriate revision sequence. And then we can consider things like, what is therefore necessarily true or necessarily brought about by such sequences? Here's the modal version, just replaces the successor stage by just using the probabilistic modal structure. Okay, so let's just note some things about these sequences. First of all, they exist. That's a good thing. This limit rule that we imposed is always going to be satisfiable. Well, because we restricted it to closed sets, that does our job for us. Just being a bit more careful about it, it says the set of all closed sets which are nearly stable has a finite intersection property, just because there's enough. Just you can always just pick one that satisfies any finite number of these things. So there'll be something that satisfies them all because the topology is compact. And the limit criterion just says pick something that satisfies all these things that are closed and nearly stable. So this relies on that the topology is compact. So that is at the moment relying on Tikhonov theorems to get because we've got this is our space. To know that this is compact using Tikhonov theorem, it's not clear that we're therefore getting a constructive method for writing out any one of these, and that's something that's maybe a worry, and it's something to consider. And moreover, there are infinitely many hypotheses satisfying the limit criterion, at least for the relative frequencies, and like there might not be infinitely many in the other one, but there's not necessarily going to be one. There's probably not going to be one. So we've got lots of choice of what to do at these limit stages. But I would say don't think of it as a construction of a sequence, but instead think of it as a criterion on sequences being revision sequences and seeing what they bring about. I've said this already. Every stage has the probability thing being finitely additive and the truth bit being maximally consistent. This is a divergence from the traditional revision theory, but it can lead to some really, I think it gets you really interesting theories out. I think if you're looking at possible extensions of probability and truth, the only extensions of a truth predicate that are reasonable are ones which are maximally consistent, because if something is true and its negation is, or if something is not true and its negation is also not true, that's not really a truth predicate. So this is an interesting feature and one that I like. And what's interesting is we didn't plug this in. We didn't explicitly say the limit stages need to be probabilities. It just fell out of the definition we gave. But they don't satisfy this countable additivity feature, and the truth thing is omega inconsistent. These are not closed properties, so there's no reason to expect them to be brought over to the limits. And this is, you can show it by this influential result by McGee, which I'm not going to go into, I think. Also, this holds for the modal version, and it doesn't, and it only needs convex sets. So our weakenings of it would also have this feature. Here's a feature that motivated Hannes Sleitgeb in developing his construction. It's that the probability of phi is the same as the probability that phi is true. Now we can't get we can't get phi if and only if phi is true, because that's inconsistent with just classical, with classical logic, and the t by conditional thing. But we can get this, they have the same probability. And also this implies, for example, that the probability of the liar is a half. We get this in all the relative frequencies constructions, which are the ones that Hannes Leitgeb considered. And the reason is that the probability of phi and t phi converge together, or the probability, the difference between them converges to 0 along the finite stages. So by this near stability thing, we sum that up to being, at the limit it would have the probability of phi minus probability of t of phi would be equal to 0. Now it doesn't hold in the modal case, and it's not just that it doesn't follow from the definitions, it's inconsistent with the setup we've got. So for example, if you've just got a world which is only has one possibility that it's considering, then the probability, this should be liar. The probability of liar plus the probability of liar is true is always going to be 1. It's always going to be that either the probability of liar is 0 and the probability of t of liar is 1, or the other way around. So by our definition, we will have that at limit the probability of phi plus the probability of t of phi is also going to be 1. So we don't satisfy this probabilistic convention t. Now, since Leitgeb was particularly interested in having this, one can say, okay, you can get that if you want to. Here's how to get that. You drop the characterization I gave, and instead you want something, the limit stage is a probability function, satisfies this near stability criterion at least for these interval properties. And this will get the really essential feature that if it converges, then it should have that probability at the limit, and this probabilistic convention t. And you can get these three things by essentially taking a Banach limit of the previous truth values. And that's what Leitgeb is doing in his version, and you can also do this in the transfinite version as well if you want. But I don't suggest doing that because I don't think probabilistic convention t is that is as nice a feature to remove the kind of smooth and nice features we get out of the limit criterion we considered. Since this is always satisfied beneath that limit, doesn't it make more sense to have it also satisfied at the limit than this probabilistic convention t? But that's a that's a choice matter. And if you want probabilistic convention t, you can get it. This is something I just added, so if it's wrong then. That this near stability definition, you might think, sure, it makes a difference at omega squared. But does it make a difference to whatever is nearly stably satisfied after we've done the whole ordinal sequence? Well, in fact, it does. It doesn't get washed out that easily. For example, a sentence which says some iteration of t's of the probability of liar equals the probability of true of liar. Now that sentence is not going to be nearly stable unless you have the near stability limit rule instead of just the stability limit rule. Because you can find relative frequency revision sequences where limit ordinals like omega squared, ones that aren't of the form something plus omega, don't have the probability of liar equals the probability of t of liar, because there'll always be some sort of finite stage, not finite, some limit plus 1 stage where that's not satisfied. Okay, so this does actually make a difference, this alternative limit rule. I'll quickly just sort of present in a more kind of systematic way some of these features by presenting some theories for these sequences. Now what I said originally is we want to find out about truth and probability by doing this revision sequence. And the liar sentence goes true, false, forever. What can you find out about truth? Well, for the liar, maybe not so much in that thing. But some sentences don't end up always oscillating. You can get certain facts about that end up being stable or nearly stable. And these are maybe features of truth and probability that are brought about, or that we can now know via these revision sequences. So there's a number of different kinds of things you might be interested in. One are, what's nearly stable in this whole sequence? The other is, what's stable after this ordinal length sequence? And the third one that's interesting in our kind of context is, what's stable for limit ordinals in this sequence? Because the limit ordinals have some really interesting features now. And that in the usual revision sequence, they're sort of just thrown in there to sum up things. But now we've got like nice models being like, you now come up with nice models at the limit stages. So just presenting some of the theories for those. So this is whatever's nearly stable in the relative frequency revision sequence. So you've got things like rules for truth, saying, for example, t of not phi if and only if not t phi. Also, t of for all x phi of x if and only if for all x t of phi of x. There's some numerals and variables and stuff, and they need to be sorted out with that. For probability, you have that probability is a finitely additive probability function, and that it satisfies this this n additivity. And the reason this wasn't satisfied at limits, but because we're considering near stability, we can sort of ignore that. And you've got certain introduction and elimination rules. So if phi is nearly stable, then so is t of phi. And here's a nearly probabilistic convention T principle. And this is basically a theory that Hannes Leitgeb presented in his paper. Good. Oh yes, I wanted to say this is in no sense a complete theory. This is just some things that are satisfied, some things that are nearly stable. And there's no hope of coming to a complete theory. It is just too complex. I don't know if I really want to go through this. So yeah, there's slight modifications if you're doing the modal version. What's also interesting in the modal version, what just happened? Okay, is given particular frames, you can also have additional axioms to be added. So for example, if we have a frame where each world is certain of its own accessibility measure, then, and this is sort of an introspective world, it sort of knows what it thinks, something like that, so an introspective frame. Then we can add a principle. If it's true that the probability phi's are, then the probability that the probability phi's are. That will be stable, nearly stable, everything, in such frames. And reasons why this is then interesting is, for example, it's been considered by a number of people that this principle without the t is inconsistent with axioms of probability because of this probabilistic liar. But now we can see all that was just missing is you just didn't have a t predicate there, and it's something like the liar paradox was just screwing it up. But now if we have the truth predicate there, we can express this principle to describe these features, to describe these structures. Some theory for stability is interesting here because we have, in a sense, nice limit stages that the usual revision sequence doesn't. So in the usual revision sequence, what ends up being stable is quite a weak theory. But here we have things like P is a finitely additive probability function, and T is maximally consistent. And this theory is omega consistent, whereas these near stability theories were omega inconsistent. So an omega inconsistency you might think is a very bad thing to have for truth. So here we get a theory that's much stronger than the usual stability theory, and it's omega consistent, which is cool. And one can also get interesting things satisfied at the limits, interesting theories at the limits. So for example, now we have probabilistic convention T as an axiom here. And sort of, if something was provable in the near stability thing, then it should be true. And this is, in fact, it's not even stable at limits, it's just satisfied at all limits, because I haven't added in anything that's not satisfied, like at omega or the earlier ones. So that's kind of the brief sum up of some theories and these constructions. Quickly, just some future questions. This was just a list of some things I'd like to think about. One thing is this: I moved from stability to considering near stability. And this was particularly motivated in the framework because of the flipping up to 1 all the time. If you consider stability, you don't get enough. But why not consider more? So for example, at some bigger ordinals, you might get not only after a finite shift something's always satisfied, but after omega shifts it's always satisfied. Now to do this, you have to make sure that the ordinals which you're considering shifts by don't go past the limit ordinal you're considering. So yeah, that's something to be looked at, is whether we can get extra stability conditions and whether that actually, so characterizing what stability you're interested in, and whether this actually leads to anything new and interesting. That's just saying this transfinite successor stage was weird that we defined. Let's consider alternatives. For example, this one that Leon Horson's working on. And I mean, now the limit rule we've suggested is quite complex. Yeah, and what's the complexity of the set of stable, nearly stable sentences? That's something I've not thought about at all, but it would be interesting, and it's probably quite complex. So just to sum up what I've done, I've presented 2 revision sequences, one which used this notion of relative frequency in the revision sequence, which gave us this semantic notion of probability or degree of truth, and one which used this probabilistic modal structure in the background to give us some kind of subjective probability. And what we found was kind of interesting and different to the usual revision sequence is that the topology, or not topology, I'm not sure if that's the right way to write it. When we have probabilities and real numbers, we have things like convergence in a way that we don't have with truth values. All they do, the way they converge to some truth value is end up being fixed on the truth value. But when we have probabilities around, we can get like other interesting notions of convergence. And those are natural things one should also put into the limit rules. And by considering these more restrictive limit rules, we went for the fully restrictive one, being as restrictive as possible in a sense. It's just the closed properties and only the closed properties that one can ask to be taken over to the limit. So by considering this restrictive limit rule, we came to some really interesting revision sequences and theories from it. And that was the limit rule, which was particularly, that the closed properties of hypotheses and nearly stable beneath limits should be reflected at that limit. So, thank you.
Questions or comments? Yes?
You have this theory where probability 1 in and probability 1 out. And I think you had commutation with respect just to the propositional things.
Just for the language without truth and probability.
Yeah, I
Sorry,
mean,
what do you mean?
I mean the
Do
first.
you mean this one?
Yes, I mean that. So what happens? So if commutation, so there's no interaction with respect to the quantifiers.
No,
So that's probably
it's only finally additive.
that's probably crucial.
Sorry?
That's crucial that there's
Yeah.
no interaction. Otherwise,
Uh,
would you get omega inconsistency?
Yeah, so that, I mean, in this version, I mean, the analogy is that you have the truth in and out and commutation with the universal, and that's kind of important, or that basically gets you omega inconsistency. And probably, yeah, the same thing's going to happen here. This, yeah, probably if you had commutation with the universal as well, i.e. this countably additive property, and these two, then yeah, you'd probably get omega inconsistency.
Okay.
There's something I don't think I quite understand about how this sits in the world of logic and probability. What happens to conditional probability here? Is it built in, or is it a hugely new question?
Well, I mean, obviously by the conditional, the ratio formula, you can get some things about conditional probability. I haven't considered more than that yet, but there's some kind of basically, I haven't really thought about conditional probability explicitly in this, and to add it in, it's not clear that by adding it in just like that, it gets you what you want. So, for example, if we have these probabilistic modal structures, let's say there's two worlds, you're equally sure, sorry, they like uniform distribution over them. The probability that the coin lands heads is a half, and the probability the coin lands tails is half. Now, what is the probability that the probability that the coin lands heads is 1 given heads? I mean, from the kind of setup and using the ratio formula, you get that that's 0, but it should really be 1.
Yeah.
So there's a lot of further things that need to be thought about to add in the conditional probability here. Probably in the relative frequency one, it would be quite easy, but I haven't really thought about it too much.
Okay, I think we are out of time, so let's thank the speaker again.